Look at a standard financial ledger. It is highly structured, standardized, and based on settled transactions. Now look at a climate data model. It is probabilistic, geographically dependent, and inherently fluid. The transition to a net zero economy is an economy-wide structural transformation, changing the assumptions that underpin investment and valuation. This shift alters the foundational baseline for creditworthiness and capital allocation across all asset classes. For asset managers, processing these changes creates a profound obstacle known as the green data gap. This gap persists because legacy information architectures are poorly suited to accommodate the messy, probabilistic nature of climate science. The objective for an enterprise architect is to build systems capable of translating the raw physics of climate change into the quantitative language of financial risk. Managing climate risk involves treating environmental science as a new set of drivers within the existing enterprise risk architecture. This architectural model connects climate science to financial impacts. At the top layer, science branches into two pathways: physical hazards and transition drivers. Physical hazards represent direct disruptions to an asset's operations, including acute events like severe storms and chronic shifts in temperature or precipitation. Consider a utility company dependent on hydropower. A changing precipitation regime directly alters electricity generation, impacting operating costs and the entire revenue base. Transition drivers are different. These are economic pressures stemming from the move toward a low-carbon economy, specifically carbon pricing, new emissions regulations, and technological substitution. For an internal combustion vehicle manufacturer, these drivers manifest as competitive pressure and the potential for stranded assets as electrification mandates take hold. Whether a risk originates from weather patterns or technology laws, both pathways funnel through economic transmission channels to reach a final set of financial risk outcomes. These impacts eventually manifest as familiar metrics: credit migration, asset impairment, market repricing, and liquidity crunches. Legacy financial data is based on transactions, but climate data is inherently estimated, model-derived, and geographically dependent. Because climate data is probabilistic, it requires strict data lineage. Every emissions figure or hazard projection must be traceable. Systems must track the metadata beneath each number, including data provenance, specific estimation techniques, and the organizational boundaries used in the calculation. Two data sets can report different emissions numbers for the same asset without either being wrong. The difference often comes from different methodologies or reporting periods. The architecture must preserve this context rather than reducing a complex range of possibilities to a single number. This requires a shift from simple data governance to rigorous model governance. Using AI to fill missing data gaps can create a false sense of precision. Without strict governance, AI models can amplify the uncertainty inherent in the underlying information. A mature architecture treats methodological limitations and confidence intervals as actionable information. Historical financial data cannot predict the economics of a transition that hasn't happened yet. Asset managers need simulation engines capable of evaluating multiple alternative futures. This requires a scenario engine that stacks a scenario repository on top of risk and financial impact models, eventually outputting to portfolio analytics. The critical principle here is the structural separation of scenario assumptions from the core calculation logic. This modularity allows risk teams to evaluate alternative futures, comparing orderly and disorderly transitions, without rebuilding the underlying technology. This allows an institution to test how specific stressors, like prolonged drought or abrupt carbon taxes, would directly impact portfolio value. An architecture built for dynamic simulation is the only way to accurately price long-term, nonlinear climate risks. Global frameworks like the TCFD act as catalysts for this transformation, but they are not the final objective. Building isolated data pipelines for every new jurisdictional mandate creates a brittle and inefficient environment. The goal is regulatory agility, achieved through a unified data foundation independent of specific rules. This distinguishes between underlying facts, analytical methodologies, and the configurable regulatory layer. Organizations collect environmental facts once, governing them centrally to support multiple compliance capabilities. Separating intelligence from localized formatting prevents the architecture from collapsing as regional disclosure laws mutate. The objective is to embed climate analytics directly into the active workflows where capital allocation decisions are actually made. Portfolio managers can then evaluate transition sensitivity and hazard exposure in real time, integrating these factors into every trade. This approach transforms environmental signals into financial risk factors, exposing them through analytical platforms and decision support tools. Bridging the green data gap allows an institution to move beyond compliance, turning climate intelligence into a capability for pricing risk and generating alpha.